So in impedance matching, we started with the concept and we majorly looked at the two things, right? That for the first thing is that, right? Whenever we say we are trying to match the impedance, it is between a source and the load, right? They will have different impedances, right? Just to match them, we are supposed to use a circuit which matches the impedance. Where variety of options do exist, but right, the most suitable one is to use a transmission line. Correct. Till here we had discussed yesterday. Again, we saw that, right? If you use a transmission line, there is an advantage of the matching circuit being non-resonant, right? It's not going to vary with the frequency, right? The impedance, right? But there are some catches, right? We'll come back to that today. Okay, we'll see that, right? Is it true for every transmission line, or is there any difference, right? So we'll check that first today, and then we'll proceed further. Okay, so the two major transmission lines that have a lot of applications, right, or the special properties are, one is a quarter wave line, and another transmission line is called as a half wave line. Okay, so there is a line called lambda by 4 transmission line. This is referred to as a quarter wave. Okay, there is another one that is lambda by 2 transmission line. Yes, as we call it half. Right. Now, so in case of, let's look at the quarter wave first. Okay, so in case of a, I'll write, so in bracket I write, this is what we are going to write it as QW. Okay, so in case of a QW line, we have one very important relationship. We already have seen that, if you remember, right? There is one relationship, that is Z naught is can be calculated as a square root of ZL into ZS. Okay, so this equation, do you remember? Otherwise, some of the books will write it in the following format: ZS equal to, it's the same equation. Okay, so Z naught squared divided by the ZL. Right, so here the ZS is, other terms we are very familiar. Z naught stands for the characteristic impedance, ZL is the load impedance. Okay, but what is ZS? ZS is the impedance of the source looking towards the load. When you look towards the load at a given point, right, this is what is the impedance that you see. Okay, yeah, you can consider that. Okay, so I can write as this is the impedance of the source, right? Impedance of the source looking, correct, looking towards the load. So you remember this equation, right? Okay. Now let us look at an example to make things very clear. How do I utilize this equation in case of a practical problem? Okay, now let us consider a scenario wherein I have, say, an antenna. Okay, so I'll try to write, maybe this is, okay, I try to denote an antenna. Preferably this is a, let's say this is a dipole antenna. Okay, so let me give a small space here. Okay, fine. Okay, so this is an antenna, right? And I have, okay, I want to show you a different application. Previously, we discussed that, okay, between a source, which can be a circuit, and a load, which can be another circuit, right? I'll show you a different application today. So let me say there is a transmission line which carries the power. Okay, this is carrying the power from some other circuit. Okay, maybe before this you have a uh, amplifier. So that amplifier amplifies your signal, right? The radio frequency signal, whatever it is, right? And it is carrying this till here so far. Okay, but again we have some. You may face a problem that if I draw if I use a single transmission line, that is not sufficient to match my impedance. Let us say, okay, right, using a single transmission line does not serve my purpose. So what I use two transmission lines for impedance matching purpose. Now I'll show you the exact thing that's going to happen inside our transmitter circuits. Okay, so see, on this right, on the rightmost side, whatever I'm seeing is a okay, I'll write here, this is dipole antenna. Okay, that's this part. Okay, fine. Now you see the antenna has a feed, right, which is going to be one transmission line for the time being, right? I'll directly tell you how, what I'm using, but actually we can talk a lot about this, but directly I'll write the answer. I'll not discuss further. This is the application. Okay, this is a lambda by 4 line. Okay, so here I'm using a main transmitter. This is a main transmission line. So on this side I have some amplifier. Okay, there is an amplifier which feeds to the main transmission line. Okay, now so this main transmission line, I assume that there is a Z0. Okay, and the dipole antenna has something which is RS. Okay, I'll write RS slightly before this. So let's say this is the RS. Okay, that's near the dipole antenna. Now, what should be the impedance corresponding to this transmission line, the lambda by 4 line? Let's call that as some Z0 dash. That's a characteristic impedance of the lambda by 4 line. Are you okay with the notation? So there is a dipole antenna with a resistive input impedance. Okay, so that is RS. So you can see the RS written over near the dipole antenna, just to say that that is a resistive impedance of this. Now this RS has to be matched to the main transmission line, which has a characteristic impedance Z0. Right now, as I told, you have multiple options. I'm just showing one example that how can I use the lambda by 4 line. That's all, right? It's not that only this is the answer. Yes, you can go for other transmission lines as well. But my intention here is to show that you can use multiple transmission lines as well for the matching purpose. That's all. Okay, so by using a quarter wave transmission line, normally if you remember the word quarter wave transformer, right? The word is transformer, right? How do I choose, right? So this part is the, okay, I can write quarter wave transformer, right? I need to do only one calculation, that is how do I match this? So that Z0 dash should be equal to the root of, using the above equation, okay, Z0 into RS, right? So that's a very simple application. You can simply use the fundamental characteristic of our quarter wave line, which you see here, Zs is equal to Z0 square by ZL. Otherwise, the Z0 of your line is equal to ZL into Zs, root of ZL into Zs. So I'm using that property here to match this. So like this, you can match. This is one simple application. Okay. Now I have a question here, right? What problem do you see with this kind of matching? So the hint is that we discussed one point yesterday saying that there is something called as non-resonating, right? So that's a hint. You have to think in that direction. Do you have any problem with this part is my question. Uh, yeah, right? So actually, you are close to the answer. That's almost the right answer. Okay, perfect. So as we know, non-resonating means you can change your frequency, right? When you change the frequency, the characteristic impedance Z0 will not change, right? That's what is non-resonating. Hmm. In this case, that is right, correct. So I am fixing the lambda by 4 by looking at a specific lambda value, correct. Only for a given lambda, this line is lambda by 4 line, right? Which means it is fixed for a given frequency, correct. For a given frequency, this looks like a lambda by 4 line for. But when I say I'll change my frequency, right, this is no more lambda by 4. So that's the problem, right? Your answer is right. You said that the Z naught is going to change. Yes, perfectly. So the Z naught dash what you have calculated will change if you change your frequency of your signal. So that's a problem. And again, as I told at the beginning of today's session, I mentioned that there are some catches, right? It's not true for each and every line. Some lines will not satisfy. Okay, definitely. So it will be there. It's so any rules is not universal. Some things will, some points will be there which will not satisfy. We have to compensate that somehow. So again, there are options to satisfy that. You can use multiple lambda by 4 lines calculating what are the various frequencies you can use, you might use. Okay, so you will make the signal to propagate through various lambda by 4 lines which kept parallel over here. Okay, so that can be made, using which you have a solution. That's it. That's one of the possible solution. Again, that is called as multiple stages of lambda by 4 line. It is called as broadband impedance matching. There is a whole new concept coming up, right? Again, that's not in our syllabus what we are studying, right? But when you go for the actual manufacturing of some circuit where you have antenna and a circuit present over there, right, with a wide band of frequencies being transmitted through the antenna, you have to study a concept called as broadband impedance matching. Okay, so I'll quickly write one disadvantage over here just for your reference, right? The lambda by 4 lines, they okay, I can write they suffer, so they suffer from sensitivity to frequency changes, right? So whenever you change the frequency, we have some issues, right? Anyway, we don't have to discuss further, we understood, correct. Okay, right. So we have a solution that is using multiple stages of lambda by 4, right? Okay, so we discussed the solution as well. As of now, that solution is not required for us. Okay, let's move further. The other one is the uh, lambda by 2, and we are going to call it as a half wave. Okay, so I'll just call this is H W, half wave. So this is the half wave transmission line. Right. Now, as the name suggests, it's going to have a lambda by 2, right? Again, this is one of the very famous transmission line for impedance matching purpose. Okay. So, let us say the load is placed at the far end of the half wave line, and the input source impedance will be equal to the load impedance. Okay. It's actually a property of half wave line that is applicable whenever you use lossless type of line. Okay, so this is where we use the lambda by 2 for the matching, right? I'll write the sentence which I just mentioned. Okay, so okay, I can write, so if the load is placed at the far end of the lambda by 2 transmission line, what happens is the input or the source impedance will be equal to the load impedance by the property of a lambda by 2 line. So this is a property of the half wave line, and right, normally applicable to the I can say low loss or the lossless. Okay, you can apply this over there. Okay, now again, as the name suggests, it is lambda by 2, right? So there is the frequency dependence. Okay, are you okay with that? Right? So lambda by 2 suggests that the it's fundamentally frequency dependent. Okay, right, now where do you apply? So this, the property which we have discussed just now is very useful when we need to short circuit a line at any point, okay, which is physically not possible. In the sense, I cannot actually bring a short circuit in place. Okay, right, that's uh, whenever I want to perform such a task, right, I'll give an explanation. I'll give you another explanation, right? So this is how it's going to work, right? So how do you achieve that? I'll repeat the my last sentence, right? The previously discussed property, right? What is the property? You can see that if the load is placed at a far end of the lambda by 2 line, into input impedance, what when you look into that, that is a ZS, looks like your Z not only. Okay, Z not equal to ZS, right? So the application I mentioned here is like I want to have a short circuit, okay, of a line at a particular point, right? Physically I cannot bring a short circuit. Okay, something like I have a transmission line at this particular point. I want to have a short circuit, let's assume, but physically I cannot connect, right? I don't have any authority to short circuit the line over here, right? So under such case, right, I can use the lambda by 2 line, right? So what I do in order to achieve this kind of short circuit, right, you place a short circuit on the line at a point, okay, which is half wavelength away from the point. In the sense, you terminate this line with a short circuit at the end. Okay, this is allowed, this is allowed, this is the end point of your transmission line. You can have a short circuit, you can have open circuit, no problem. Okay, but now you see, if you keep this length as lambda by 2, by the property of lambda by 2, if there is a impedance 0 here, right, 0 impedance here, you can see the 0 impedance here also, correct? That's what this whole sentence, what we discussed so far, right? So you see, that's the application, very widely used in the practical scenarios. Okay, I'll write that point here. So there is one very important property and its application. Application, I wrote a diagram, right, already. So let's quickly write that. Okay. Okay. Uh, all right. We can use this property of the half wave transmission line when whenever we need a short circuit, okay, at a particular point on the transmission line. Okay, I will also write which is practically not possible if the point, whichever point you want to have a short circuit, is in the middle of a transmission line. Like this case, it's somewhere in the middle. I cannot, right? I cannot do a short circuit over there. So what is the solution to achieve this, right? To achieve this, as you know the answer now, we try to uh, put a halfway line, okay. To achieve this, we place a half wave transmission line with short circuited end, right, next to that point, next to the desired point. This is the option, right? So you see that, right? We can see on the right hand side of the transmission line, I can place this one, the short circuit, right? I don't want to write a 0 here. Let me make it as a SC, short circuit. Place the short circuit, right? Lambda by 2 distance away from that. In the sense, I am placing a lambda by 2 line over there. Okay. Now, so also we have a lot of applications which can be applied, right? To convert a given transmission line into an application. Okay, okay, I don't want to go with the directly theory part, right? That's going to take a lot of time. Let's compress that. But this application you need to remember. Okay, so I'll directly go with the types of the transmission lines. Okay, we'll make a table. Okay, types of transmission lines on one column, and the application on the right side. So the first one that we are going to discuss is a, let's say this is the one. Note that there is a short circuit at the end, SC I'll write, and you also need to know what is this length. Okay, so depending on the length and the type of the load, right, we have applications built. Okay, so now this is the first application, that is lambda by 4 line with a short circuit. Okay, where do you use this? Whenever I want to have a parallel resonating circuit. So if you remember a parallel resonating circuit, you can have one capacitor. This is the simplest one. Okay, one capacitor, one inductor, C and L in parallel generates a parallel resonating circuit. So you want to have this, what is the option in case of a transmission line? Simply use this. Okay, that's the very fundamental application, right? Next one, uh okay, next is, so this is a lambda by 4 and it is open. Okay, so this is open circuit and the lambda by 4. So the application, whenever you want to use it as a series, so when the length of the transmission line is lambda by 4 and it is terminated with the open circuit, this will be used as a series resonance, right? So series resonance means one inductor in series with the capacitor. This is the practical circuit, LC. Okay, so that's the application. All right, let's move further. The third application, let me say I want to use a transmission line whose length is not lambda by 4. I'll say it is lesser than lambda by 4, so I can make it shorter. Okay, so the total distance was lambda. Okay, so sorry, total length was lambda by 4. Now we have reduced this. Okay, so this, yes, so 0 less than or equal to okay, L less than lambda by 4, and you can note that there is a short circuit. So if you use this, this is a simple inductor. Okay, you can, when you want just to bring an inductor in place, just use this. Okay, now, so the idea is that when I have a very small place and I want to bring an inductor, you don't have to go for actual inductor which are very huge in size, right? The inductances are very huge, right? You don't have to go for that. You can use the transmission line itself to yes, 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 yes. Very similar case. I have the same shorter length line, but it is open circuit. Okay, this is OC. Yes, yes, yes. As you guessed, 0 less than L less than lambda by 4. This is going to be a capacitor, right? Simply, yes. Okay, there is another option. What happens if you extend this line further, right? So that is fifth one. Now, okay, let me write this. Let me make the length larger. Okay, so this is a larger length now. And I have a short circuit. So this is L greater than lambda by 4 and you have a short circuit. Now this is also a capacitor. Okay, so you see length greater than lambda by 4, you need a short circuit for capacitor. Okay, now you can definitely guess what's the next one, but open circuit, correct? So yes, this is the length. So those are the applications we can use with the special lines, that is lambda by 4 and lambda by 2. Okay, so out of which again you can see most of the applications are based on the lambda by 4 only. Okay, so L greater than lambda by 4, this means it is an inductor. Okay, is it fine? Okay, now yeah, the next applications will be directly, we will discuss about the stub matching concept. Okay, but before I go ahead with that, I want to solve the problems based on whatever we discussed so far. Okay, because a lot of equations we studied. So let's change, instead of just discussing on, keep on discussing the theory, let's shift to the problems part. Let's finish the uh, important types of problems based on whatever we discussed so far. Okay, everything, every related to every concept we studied so far, I try to solve at least one problem. Okay, uh, that's what is that's what I'm going to do, right? After that, there is a homework part coming up. That will be you will take up last 5 years question paper from your syllabus, from your college, and whatever we problems we solve, similar problems from the same chapter, whatever that came up, you will write, you will solve, and you'll submit to me. I'll go through that and I'll get back. Okay, so that's how it works. 50% from my side, remaining problems you can solve by yourself. Okay, and anyway, I'll check all of them and I'll get back. Okay, so you can take up something like 1 week of time to do that, right? Not in hurry, right? Take your time, solve carefully, but I want you to solve every problem that is present in your last 5 years of question papers. Okay, so that's what I expect from you. All right, so let's start the problem. Okay, so this is problem number one. Okay, a transmission line has a resistance of 8 ohms per kilometer. Okay, then inductance of 2 millihenries per kilometer. Capacitance 0.002 microfarads per kilometer, and a conductance of 0.07 microsiemens per kilometer. All right, now I want you to calculate the yeah, we'll try to calculate whatever possible. Okay, characteristic impedance. I want you to calculate the attenuation constant. I want to calculate. Okay, at 2 kilohertz peak, and I'll add another part to this. If a signal of 2 volts is applied and this transmission line is terminated with the characteristic impedance. Calculate okay, calculate the power delivered. This is very interesting. Calculate the power delivered to the load when uh, uh, transmission line is okay, of length 500 kilometers. Okay, right, almost a majority of the things I try to cover in this question. Okay, so maybe in your question paper you don't get everything like this, right? But a part by part. Okay, right, but anyway, I try to. Yes, in this case, you can see that the ZL equal to the Z naught value itself. Right. Okay. So let us. All right. Let's start with the. Yes. Yes. Sure, please. Okay. Do one thing. All right. I have a solution for that. Right. So anyway, normally you will put this into the calculator into the complex mode, right? You yeah. You can do that. Let me check with my calculator once, and I'll answer you. Just one second. Two plus one second. Okay. Now, so if you have something like maybe 2 plus 3i, I will convert that into say r angle theta first. Okay. 3.6 angle 6 square root of 3.6 at an angle 56 equals to. So, okay, no problem. I'll tell you the easiest way. Okay, so what you do, you calculate the inner part, right? Whatever is inside the square root, right? You first calculate that, right? And give me the answer. How much you get when you simplify that? So this is still a one second. I'll write just perfect. So what's that answer? Please come back again. This is under root 1.04 into 10 to the power 6 at an angle minus 17.49. Okay, now this 497, all right, degrees. Okay, now what happens whenever you have a square root, the r theta format you have, right? The r becomes root of r, right? So what is that root of r? You have to calculate only this part, that is root of 1.04 into 10 to the power 6. Okay, and the angle becomes like this. Whatever you have angle, right, that is minus 17.497 you have, right? Divide that by 2. Phase is half. Root as it is. Magnitude will be you have to take a square root of the magnitude. Okay, because it is square root. Okay, when you have a square root, angle becomes half. Okay, that's the idea, right? How to calculate, how to solve the square root of a complex number. Yes, sure. Please take your time. Correct. 1.01 into 10 to the 3 at an angle minus. Perfect. This is Z naught. So answer is ohms. Measure in terms of ohms. Okay, first part is done. Now the second part of the question says that measure its alpha and beta value. Correct. So Yes, gamma is equal to, I'll try to, okay, what's the equation? J omega L into G plus J omega C. Okay, let's substitute the same way what we did earlier. Okay, so this is under root R plus J omega L gives you 8 J 2 4 pi into 10 to the 3 into 2 into 10 to the, right? Okay, yeah, this is what you need to simplify. Okay, first you tell me what you get under the root. 6.68. Okay, 162.18. Now you know how to simplify, right? Okay, give me the uh, last answer, final answer. In first you give me in r angle theta itself, okay, but later on we'll convert. 0 point. Okay, I'll write that way. So 25.7 into 10 to the minus 3 at an angle 80, 81 point something, I guess, right? Because 162, right? 09 degrees. Okay, this is gamma. Now I want this to be converted. I just want to equate this with alpha plus or minus j beta, right? So you need to convert this into, this is in the polar format, convert into the rectangle. Okay, so that is 3.98 into 10 to the minus 3, 0.025. Ah, yeah, 5, right? Now that means I can equate, right? You can compare it with the alpha plus or minus j beta. Right. So alpha value is equal to 3.98 into 10 to the minus 3. If you remember, this is Napier's. Okay. Standard notation is NP. Again, this is per kilometers. Okay. And you have the beta value. It's a constant, phase constant, right? 0.0253 phase. So it is a radians per kilometer. All right. No. Okay. The first half of the question is over. Then I actually extended the question by a second, by adding a second part. You see, right now we apply a 2 volt source, 2 volt uh, voltage source at the beginning, or as a source we connect. Okay. And on the load side, you connect the device with the same impedance that is equal to the Z naught we calculated. Absolutely fine. Now the question is, if this line is of length 500 kilometers, how much power gets delivered? Okay. Yes. So you see the power equation still remains same. Power can be measured as either I square into R. Okay, P equal to I square R is our fundamental equation. We are not going to change that. But which current you want to apply, you need to think, because there are many currents. I have a current that is being supplied, which is IS, or a current that is actually passing through the load is IL. Mostly we are going to use the IL because we are looking at the power on the load side. So you have, that gives you a hint that you should calculate IL somehow. Okay, first thing. Again, so I need a resistance value, right? You have to calculate a resistance that is corresponding to the Z naught over there. Okay, fine. We'll see, we'll think about that later. Okay, so I need the resistance value over the Z naught side, and I also need the current. Correct? Okay, so let's look at, first we'll try to solve the current part. Okay, so current in the sense, I know that what is the, how do I calculate the IL? Load current is equal to the supplied current into e to the power minus gamma L. Correct? Do you remember this equation? Right. I have to use this to get the IL part, but I don't know IS at first. Correct? So let's go for the IS. Correct? So, but I need to calculate the IS first. Let me hold on to this equation number 1. So let's calculate IS. IS is nothing but the current that is flowing into your transmission line from the power supply. So current is nothing but, I just have to apply the same equation. I is equal to voltage by impedance. Right? So voltage is supply voltage Vs divided by, now you see, when you look into the circuit, when you look into the transmission line, I am able to see the Z in, right? Z in, right? But here already mentioned it is Z not only, correct? The transmission line has this same thing. So I can actually write Vs by Z naught characteristic. So apply that. That is, this is 2, no angle given. So 2 angle 0 divided by, just now we calculated the Z naught value is actually, you can see Z naught is in this format, right? 1.01 into 10 to the 3. Just write that. Okay, 1.01 into 10 to the power 3 at an angle minus, sorry, I forgot, 8.75, I guess. Let's just check. Yeah, 8.74. So minus 8.74 degrees. Okay, it is simply 2 divided by 1.01 into 10 to the 3. That 10 to the 3 will become 10 to the minus 3. So 2 by 1.01. That's what we want. One 1.95. No, I prefer in the R angle theta format. Okay. At an angle plus 8.74 degrees. So these many amperes. Anyway, I can write it as milliamps by removing the 10 to the minus 3. Absolutely fine. This is okay. Now you calculate what is the current that is flowing at the load, right? Substitute in equation number 1. IL is equal to IS, that's this value, 1.98, 10 to the minus 3 at an angle 8.74, right? This you need to multiply with e to the power minus of, anyway we have the gamma value. You are free to use whichever format you want, you can substitute. Okay, so the, I think the gamma came to be, let me just go back. I prefer substituting in the R angle theta, but you are free to use whichever format. 25.7 into 10 to the minus 3 No, at an angle, I think 80 something, because we took a square root of that, right? You see here? Yeah, okay, that is 81.09. This should be multiplied by your length, correct? So into 500, okay? Don't put a kilo over there, because everything, as I told, length is fixed, right? Length is always kilometers, so I don't have to worry, right? Remove the kilo from that, okay? Yeah, sure, sure. Huh. Okay, okay. Okay. Okay, okay. Depends on the calculator. I'll tell you the other option. Okay, don't enter in this way. So let's try to write it in the other format. That is, I'll write the 1.98 into 10 to the minus 3 at an angle 8.74. Then you write in this way. It is into e to the power minus. So you don't write in the complex r theta format. Some of the calculator e to the power. The power, when you raise, it is expecting the alpha plus j beta format. Okay, so there are some calculators which will, that format also it is not accepting 3.98 into. Okay, I'll just write first. Then I'll tell you what to do. Okay, so please tell me what are the values. 3.98 into minus 3 ah, 0.0253. This is the gamma value, correct? Into L. L is equal to 500, isn't it? Into 500. Okay, now you see, I'll tell you. So just to solve this problem, I don't need this complete answer, first of all. Okay, why I'll tell you, because you see, in my ultimate equation, final value of the power calculation requires current square into the impedance, correct? So current square is nothing but magnitude of the current only. Okay, I don't want the whole currents equation. So when you solve this, you get the whole equation of the current. I don't want that. Okay, so what we do, let's say, since the calculator is not calculating, I'll write magnitude of IL. Okay, I calculate only magnitude of IL. Don't worry about the angle, just calculate the real part only. What is the real part? 1.98 into 10 to the minus 3 into, even in the e to the power, I have a real number coming up, that is e to the power minus of minus 3 into 500. Just calculate this. This is the other option what you have. Okay, whenever calculator is not giving you an answer for the whole expression, think that what I need actually, right? If you need only a part of it, just calculate that and write that I'm calculating only this part. All right, so that's what we need, right? So two, can you come back? 2 point, uh, right? So many amperes. All right, 2.7 into 10 to the minus 4, or 0.27 milli, right? Perfect. Okay. Now you go and go ahead and calculate. Therefore, the power delivered. Power is equal to IL square into, you see, I see I am actually writing the Z naught, but if you write a Z naught, it's not a power dissipation, okay, or the power delivered, right? Power requires actually only the, again, there are multiple versions, but this is what I think correct. Just give me your feedback, okay, or you check what has been covered in your college, right? So college syllabus, what they covered, that also you compare with what I'm teaching now. Okay, so according to me, only the resistive, so you see the Z actually has a R plus J times X component, correct, in which this component is coming because of the inductance or capacitance, fine. So that is not responsible for the power, right, calculation. Power calculation actually requires only R part, right? So what I usually do is, it's take a real part of your Z naught. This works, right? Or in this, you take a real part means you get only R, right? So that's what is actually required to calculate the power part. But I have seen that many of the faculties use Z is an impedance, so put a Z as it is, you can calculate, no issues, but the power becomes complex. Okay, that's what there will be always, right, questions being raised up, which one to be used. So power calculation is always real, because of which we are doing this. Okay, okay, just real part, right? Okay, then absolutely fine. So just substitute 2.7 into 10 to the minus 4 I square into, I'll go back to the calculation of Z to check that what is the, oh, in the Z not, right, we have not calculated the R value, so you can calculate, in the sense you can convert this into R angle theta, not, it's in the R angle theta, convert into the A plus JB. Yes, 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 calculate the real and imaginary part, that you substitute the real part out of it. 998.271, 153.47. Okay, J is already written. Okay, so this is the format, ohms. So out of which I'm going to use only 998.27. 7.27 into 10 to the minus 5. So I can make it as a micro by making it as 72.7 10 to the minus 6 watts. So that's the amount of power delivered to the load in this particular case.